Hi everyone. So in this section we need to get the derivatives sorted out for our last few functions that we don't already have shortcuts for. So these are the inverse functions. Natural log, log in general I'll show you, but mostly we'll see natural log, and then the inverse trig function. So we want to see inverse sine, inverse cosine, inverse tangent. So I want to show you kind of the trick for figuring these out. It's pretty cool actually, I think. So let's start with natural log. So I'm just going to say consider f of x is the natural log of x. And I want you to see this not just because I think it's kind of cool, but also because it's the beginnings of what we'll be doing in the next section. So we really want to find f prime of x. That's our goal. And what I want to point out here is that this function natural log of x is one that exists purely because we wanted an inverse to e to the x. So we can take advantage of the fact that we know its inverse to help us find its derivative. So basically what we're going to do here is we're going to say, well, we know that if we take e and raise it to the f of x, the natural log of x, we just get back x. That's because they're inverses. We could do it in the other order, but this one is more helpful. So e to the natural log of x is x. That's what it means for them to be inverses. And now we can take the derivative of both sides of this equation. And this trick I think we've used a little bit before, but we're going to use it a lot in the next section. So take the derivative of both sides of the equation. One part of this is really easy. The derivative of x with respect to x is 1. The other part is messy but doable. There's a chain rule here. So we have e to the stuff. The derivative of that will be e to the stuff. And then we have to multiply by the derivative of the stuff, which is just going to be an f prime. And remember, our goal was to find f prime. So we can now solve, and we can say f prime is equal to 1 over e to the f of x. But then remember, f of x was just the natural log of x, so we started off with the fact that e to the f of x is x, so we get 1 over x. So what we're saying is that the derivative of the natural log of x is just 1 over x, and that's, I think, rather impressively simple. The natural log always seems so tricky to everybody, but that's actually a really nice, easy derivative property. I do need to tack on a domain restriction here, but this is really just about making the two sides agree. Over here, we just know, hopefully, by looking at that you can't take the natural log of a negative number, so we can only have positive x's. In fact, you can't take the natural log of a negative number or 0. Over here, the 0 is implicit. We can tell that x can't be 0, but there's nothing on this side that says x can't be negative, so we don't want to be accidentally trying to talk about the slope of the natural log function when x is negative 2, because the natural log doesn't exist when x is negative 2. So we should only look at positive numbers over here. Okay, so this is like a new derivative shortcut. Memorize, you can use it for free now. I want to do just a couple of quick examples, and then I will show you the arc sine, and then I'm just going to give you the others for free. They're very similar to arc sine in how we get them, but there's some good little bits of trig review in the arc sine one. Okay, so example, I want to find the derivative of y equals the natural log of pi. Okay, so really just to make sure you're on your toes and paying really close attention, there's no variable over here. So a lot of people want to tell me that the derivative is going to be the natural log, is going to be 1 over pi, but it's not true. Natural log of pi is just a number, which means its derivative is just 0. Okay, so enough of trickiness. Let's try z is equal to the natural log of x cubed minus 7. This is one of the best things about this section. This is the last section before we're ready to do skills tests. So you get to get all of your shortcuts mixed together in this section. And I will, just like in the last section, I'll post some group work that I would normally do in class that's really nice, messy, challenging stuff. And that is great skills test practice. Oh, I don't want to say equals. Okay, so if z is equal to the natural log of x cubed minus 7, then dz dx is going to be, okay, so here's how we talk through this one. This is the natural log of stuff. The derivative of natural log of stuff is 1 over stuff. And then we've dealt with the natural log, but we have not taken the derivative of x cubed minus 7, so we're going to chain out a 3x squared. And in terms of simplify, you can even do that all in one step if you're comfortable. I would just mush that together into a single fraction. Okay, how about, I keep getting kind of uphill on you, if I have one more, g of t is equal to t times the natural log of t raised to the 5th power. Okay, so again, it's all about that big operation. Here, we would take the log of t, we'd raise it to the 5th, and the last thing we do is multiply. So this is going to be a product rule. We're going to want that second multiplied by the derivative of the first, which is conveniently just 1. And then we want the first multiplied by the derivative of the second. This is stuff to the 5th. So we're going to have 5 times stuff to the 4th. And then we have to multiply by the derivative of stuff. Derivative of natural log of t is 1 over t. So this actually simplifies really nicely. The t's cross out all together, and I have a natural log t to the 5th plus 5 times natural log of t to the 4th. You could leave it like that. I'm just going to point out that you can factor here, because I know later when we're trying to solve, people won't always spot this. You could factor out the natural log of t to the 4th, and that would leave you with a single natural log of t here, and a 5, is it plus? Yep, a 5 here. All right. So let's look, I'm going to keep this in the same video, I think. Really quickly, I will show you where the derivative, how we figure out the derivative of inverse sine. And then I'm just going to let you take my word for it unless you contact me and ask me to show you more. The derivatives of arc, cosine, and arctangent are really similar work. Okay, so let's say, start off kind of the same way. Let's say that f of x is equal to the inverse sine of x, and we want f prime of x. So we know, here I'm going to do it over here, that if we take the sine of our function, sine of inverse sine of x should just give us x. There are domain restrictions in play there, but we'll just stick with this for now. We'll worry about them in a minute. So if we take the derivative of both sides, we're going to get 1 on the right-hand side and then a chain rule on the left. And the chain rule says the derivative of sine is cosine. The derivative of f of x is f prime of x, so we chain that out. And then we were looking for f prime, so we can divide. Okay, but it's this last little bit of simplify that's actually a little more interesting. We get 1 over cosine of inverse sine of x. And that is not quite as trivial to simplify as last time. Some people would want to just quit here, but if we remember our trig well enough, it does simplify really nicely. You can write that without any trig functions. But we have to remember some triangle stuff. So inverse sine of x represents the angle theta for which sine is equal to x. So sine is opposite over hypotenuse. So we want opposite over hypotenuse to equal x when we're starting from angle theta. So I need this divided by this to be x. There's infinitely many ways to do that. The one that seems easiest to me is just make it x over 1, but you could make it 2x over 2 or x squared over x, anything so that the quotient is x. And then we can solve this triangle using a Pythagorean theorem. We'd need 1 squared minus x squared equals this side squared, so we'd square root it. So Pythagorean theorem tells us that the bottom is 1 minus x squared. And then remember what we were looking for was cosine of theta. So cosine of theta is adjacent over hypotenuse, which means this all boils down to 1 over the square root of 1 minus x squared. There is a restriction on, let me think about this. Well, I guess we can see it there. X has to be between -1 and 1 for this to work. So you'll get big-time domain problems here. If not, but that should make sense with our original function as well. Inverse sine. If you're thinking unit circle, your y value always has to be between -1 and 1, so this has to be between -1 and 1. The difference is that here you can plug in -1 or 1, and here you cannot. You'll get some problems. Okay, so let me just give you the others for free. So here's what we get. This is the last of our shortcuts. The derivative of inverse sine x is 1 over the square root of 1 minus x squared. The derivative of inverse cosine of x is negative 1 over the square root of 1 minus x squared, which makes those two, I hope, easy to remember. It's just that minus sign that's different. And then the last one, the derivative of, I'm going to switch up notations on you. Remember that all of these can be written as inverse tangent or arctangent. Oh, I'm off the bottom. Inverse sine or arc sine, inverse cosine or arc cosine. Those are the same things. And the derivative of inverse tangent is 1 over 1 plus x squared. So that one's actually a little simpler. You don't get the square root and it's a plus in the middle. Okay, so that's our last 3 function shortcuts that we need. We've got all of our shortcuts. Let me just show you a quick couple of examples here, and then we'll move on to the examples in your packet where you can practice a little bit. So, let's see if I can sneak in a couple here. Let's say we have g of y is equal to the arctan of y squared. So that's not very messy, but the powers get people in a little trouble sometime. So if I was looking for g prime of y, I'd say, okay, so this is arctan of stuff. And the derivative of arctan is 1 over 1 plus stuff squared. So I'm going to have 1 over 1 plus stuff squared, and that stuff is a y squared. So having both of them squared sometimes gets people in trouble. And then the chain rule says you're done with the arctangent. What about the derivative of y squared? And that's a 2y that we just stick out at the end. And then my simplification would just be to say that's a 1 plus y to the 4th on the bottom, and go ahead and put the 2y on the top. Okay, so there's an arctan, and I think I'll do an arc sine as well. So let's say m of t is equal to the natural log of the inverse sine of t cubed. Okay, so in this one, the last thing happening is the natural log. So the derivative, the first thing that's going to happen is a 1 over. So natural log of stuff, derivative is 1 over that stuff. Now we've dealt with the natural log, so we need an inverse sine. The derivative of inverse sine is 1 over the square root of 1 minus stuff squared. So t cubed squared is a t to the 6th. Okay, now we've dealt with the inverse sine, and the last thing is the t cubed. Derivative of that is 3t squared. There wasn't any composition, anything left, so that's it. And then again, my simplification would just be to squash it together a little bit. So I'm going to put the 3t squared on top, and I'm going to put the inverse sine of t cubed times the square root of 1 minus t to the 6th all on the bottom. All right, thanks for watching.